Hi, pre-calc students. Today we're up to trig day 4, and the notes today are going to be in your packet. So if you turn to page 6, we're going to get started on how do we solve trig equations and then some inequalities that go with them. You'll see the very first example at the top is given the function f of x equals 2 sine x minus 1. We want to solve when does f of x equal 0. So essentially we're going to set this to 0 and solve. We're going to solve over the interval from 0 to 2 pi exactly. Okay, so we're not going to use the calculator. We're going to be able to generate some exact answers by drawing some pictures of triangles, just like we kind of did in the first part of our intro unit. So first and foremost, go ahead and set the equation above equal to 0. And then once we do that, we've set f of x equal to 0. Let's get sine x alone. So we're going to add the 1 to the other side and then divide by 2. So we get that sine x is equal to 1/2. Once you get down to this stage, this should look exactly like what we did on days 2 and 3 of this unit, which is working backwards. What angles, x, would I plug in here to the sine function that give you a ratio of 1/2? Well, we got to remember that you're an all-star trig class. So where is sine positive 1/2? Quadrant 1 and quadrant 2, where sine is positive. Going to come on over here, draw a triangle in quadrant 1, triangle in quadrant 2. The angle x that I'm talking about is located right here. Sine is opposite over hypotenuse, so the opposite's 1, the hypotenuse is 2. And although it's not necessary, we can fill in that last missing side as radical 3. Same thing over on this side in quadrant 2. So the last step is, what is this angle across from 1? And the reference angle here is 30 degrees. But notice how it will say, I'm pretty sure for every example today, to solve over 0 to 2 pi, so to get this in radians. Hopefully you're pretty confident at this point that 30 degrees is pi over 6 in radians. So to get the quadrant 1 answer, we know that in quadrant 1, one of the answers is pi over 6. Okay. To get the quadrant 2 answer, I'm going to have you remember that halfway around is pi. And with a denominator of 6, this would be 6 pi over 6. So if the reference angle in here is pi over 6, how much did I go before I got to that rest of the pi over 6 that completes 6 pi over 6? Well, in other words, take halfway and subtract out the reference of pi over 6. 6 pi over 6 minus 1 pi over 6 is 5 pi over 6 is the other answer. And those are the two solutions on the interval from 0 to 2 pi. When I answer the next part of the question, it's now saying solve the same thing, but over the set of real numbers. So what I mean is this was a short interval. It was only 0 to 2 pi. There would be more answers if you extend this out over the entire domain of the function. But before I do that, I think it will make a little bit more sense if we do part C first. We're going to go to the calculator right now, and I want you to make sure that you're, first of all, in radian mode, which I am. So if you're not in radian mode, the graph will not look like you want it to look. And when you go to y equals whatever's in there right now, go ahead and type in 2 sine x minus 1. That's the equation that we're looking at for f of x, 2 sine x minus 1. And I'm going to change my window up a little bit. I want to graph this from 0 to 2 pi. So you can actually set your x values to go from 0 for x min, and then you could type in 2 pi for x max. And it won't be a surprise that when I scroll down, it actually converts to 2 times 3.14, which is about 6.28. For the y values, you shouldn't have to go outside the window. Oops, -3 to 3. That should be a good enough window to see the entire sine curve that we're about to see. And you saw how I just traced it with my finger there. That's what we're pretty much going to see when we hit graph in just a moment here. So when I hit graph, we see that the solutions are from 0 to 2 pi. We have two solutions right here and right here. The only thing is if you calculate those solutions where we hit the x-axis, it won't tell you pi over 6, but it will tell you the decimal equivalent there. So you could check that graphically that, yeah, we do get two solutions. I'm just going to make my sketch here. And we saw that the graph looks something like this by the time I get to 2 pi. So those solutions, if we check, and just to save some time, at least in the video, I'll skip confirming that those decimals match pi over 6 and 5 pi over 6. But that's what we get graphically. Well, let me come back up here to the solution over real numbers and say that this graph would continue on in this pattern forever and ever. So for example, if I extend my window not to 2 pi, but what if I go all the way to 4 pi? how many extra solutions would I expect to see? Well, there's that first part, and then it's going to get 2 more solutions by the time I get to 4 pi. If I extended to the left and I went, let's say, out to negative 2 pi, we'd get another 2 solutions on the negative side of the x-axis. So I guess the question becomes, well, like, how often do those solutions repeat, right? What's the distance from this point right here to this point over here? And same thing, this solution got repeated. How long did it take to repeat that? Well, based on what I've adjusted my window to 2 pi to 4 pi, what you might remember is something about what's called the period of a trig function. It takes another 2 pi to complete that same cycle again. So here's how we're going to write this in general. The first solution, pi over 6, gets repeated if I keep adding on 2 pi, or subtracting 2 pi for that matter, if I go forwards 2 pi or backwards 2 pi. So I'm going to write that as this, plus 2 pi n. And what is n? N is an element of funny-looking capital Z, and that means the set of all integers. So that's going to take a little while to get used to this notation, but if n is any integer, that's going to get you to all the other solutions. Keep adding on 2 pi's or keep subtracting 2 pi's, you're going to get all the other answers. Similarly, 5 pi over 6, if you add on multiples of 2 pi, whether they're positive multiples or negative multiples, where n is an integer, that's going to get you to every single solution. This is a way to write all the solutions possible. There's an infinite number of them. It's a really, it's a tough to express an infinite number of answers, but this is the best way to do it, the most concise way to list that. Okay. And then finally, the last thing says, well, use parts, there's actually 2 more parts, sorry. Use parts A and C to solve this inequality. When is 2 sine x minus 1 greater than 0? Well, if I look at the graph, where is it greater than 0? It's greater than 0 where it's above the x-axis. So we're greater than 0 in this region right here from pi over 6 to 5 pi over 6. Okay, I don't want to include the values where it equals 0, so just be a little bit careful about that. And then where is it less than 0? Well, it's less than 0 to start to the left of pi over 6, and then from 5 pi over 6 up until 2 pi. The only thing that's going to be a little bit odd about the way I list this last notation is that I'm going to include 0. Okay, 0 definitely makes this true. That if I plug in 0, you're going to get a negative number, and negatives are less than 0. But I don't want to include where it equals 0 at pi over 6. And then I'm going to do union 5 pi over 6 to 2 pi. Now, in theory, I guess I should also include 2 pi for the same reason I included 0 at the start, except look at how the interval is written. It says don't include 2 pi as part of your final answer. So I am going to keep parentheses out here, but hopefully it makes sense as to why I'm including 0 there. 0 definitely makes that true, so I don't want to exclude it from the solutions. And it can be included as a solution according to this bracket over the 0. Okay, that will take a little while to get used to, but we'll see other examples like that. All right, if you turn to number 7, same type of idea. I've given you a new function, 3 tan squared x minus 1, and we're going to solve when is this equal to 0 over 0 to 2 pi. All right, so to get started, take your equation up there, 3 tan squared x minus 1, set it to 0. And we're going to go ahead and get tan x alone. So I'm going to add the 1 to the other side. And then we're going to divide both sides by 3. So tan squared is equal to 1/3. Once I get down to this point, when I get tan squared equals 1/3, I'm hoping what's standing out to you is to get tan alone, you are going to take the square root of both sides. And when I do that, I get that tan x equals, here's a really important step. Don't forget it's plus or minus when you take the square root of both sides. The square root of 1 is 1. The square root of 3 on the bottom, I'm going to leave it as radical 3. And although you can rationalize this, don't. It's going to be much easier to figure out what the angles are here for tan if you leave it in a non-rationalized form. You'll see what I mean in just a minute. Where am I going to have solutions? Well, I'm going to have solutions where tan is positive and where tan is negative, meaning that this is in all 4 quadrants is what we get solutions in. we get the full-on bow tie, which I love. All right, so here we go. Here's my bow tie. And again, because you would ask yourself, where's tan positive? Draw the triangles in 1 and 3. But also, where is tan negative? Oh, that's in 2 and 4. It's all 4 quadrants. Okay. How do I label the sides? Tan member is opposite over adjacent. So the opposite's the 1, the adjacent's the radical 3, and that would make the hypotenuse a 2. Now, the same labels are going to happen in all 4 quadrants. So let's just start with quadrant 1, and then we'll kind of extend it from there. So what's across from the 1? What is this reference angle right here in quadrant 1? Well, it's the same reference angle that we did in number 1. It was 30 degrees, which we know is pi over 6. So the first answer that we get in quadrant 1 is, in fact, pi over 6. I'm going to start listing my solutions down here, pi over 6. Okay. What's the next solution? Well, we actually did that in the last example as well. If halfway around is 6 pi over 6, we're just pi over 6 before that, which is 5 pi over 6 is the quadrant 2 answer. How do I get the angle if I'm in quadrant 3? Well, quadrant 3 is 6 pi over 6 plus another pi over 6. Well, 6 pi plus another pi is 7 pi over 6 for the quadrant 3 answer. And last but not least, what about quadrant 4? We're almost full circle, right? Remember, full circle 2 pi would be 12 pi over 6. But I have to subtract out what's in here. I'm not quite to 12 pi over 6. What am I subtracting out? 1 little pi over 6. So 12 minus the 1 pi over 6 that I was mentioning leaves you with 11 pi over 6 for the last solution. So these are the 4 answers just from 0 to 2 pi that we wind up getting for this solution to tan. Okay. I won't have you think too much about the solution over the real numbers here, but the weird thing about tan is that instead of repeating every 2 pi like we saw for sine, it's going to repeat every pi. So this I'm not going to have you think too much about. I'm just going to fill it in quickly. But if you add on, instead of 2 pi n, the period of the tan curve, which we'll get to much later on in the year, is pi n, where n is an element of the integers, that would account for all the solutions. Okay. And by the way, I don't need to include these two, because if you add on pi to pi over 6, that's 7 pi over 6. And if you add on pi to 5 pi over 6, that winds up giving you 11 pi over 6. So it gets all the other solutions. This part is going to be a little tricky for you to get kind of a hang of, but I'll tell you, it's not really actually a major focus quite yet in this unit, so kind of just like hold off on that for now. You can fill that in as the correct solution. Let's figure out what this looks like graphically. So I'm going to set up some axes. Let's take a look at the graph. Now, the graph of tan is going to be a little bit weirder than the graph of sine. So I'm going to come over here and I'm going to type in 3. If you type in tan x, close the parentheses, and hit squared, I realize that our notation puts the squared kind of in between the tan and the x. That's kind of a standard notation of how we write it down. The calculator doesn't do it that way. The squared above the x here, okay, means the same thing as tan squared. Okay, and then we're going to do from there a -1. All right, our window, I'm going to adjust this back to going 0 to 2 pi again. I think -3 to 3, that should be fine. We have to adjust, we can, but I'm going to hit graph, see what happens. So we get 1. We get 2, we get 3, we get a total of 4 solutions here. Okay, those 4 solutions happen to be at these 4 radian values. One thing I'll tell you is that if I do go up higher than 3, if you're like, hey, does that curve like come back down again? Like if I make the y max of 10 and I hit graph, you'll see that there's actually no height I can get to that's going to make that come back down again and connect up at the top. You can keep extending that y max. They're never going to touch because there winds up being some asymptotes on the graph of tan. So we have to address that. So here's the graph. We have an asymptote here. Here's the kind of the middle part. And at the end, you get this up until I stop at 2 pi. So where are these asymptotes located? Well, the asymptotes for tan for right now are always at pi over 2 and 3 pi over 2. And it has something to do with the unit circle. Okay, at pi over 2, which is the vertical going up, 3 pi over 2, the ratio for tan, which is y over x, would be undefined. So we get these weird asymptote things to occur. Okay, so why does that kind of affect what I'm going to do in the next two parts? Well, when you do the inequalities, you're going to have to think about where those asymptotes are. So where is the graph greater than or equal to 0? It's where it's positive, which is here, 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 and there. Those four pieces. So I'm going to start by saying, okay, well, and it's greater than or equal to, so I can include the solution. Remember, the first solution is at pi over 6. So it's from pi over 6 up until, but you can include the asymptote. We can't just go from pi over 6 to the solution at 5 pi over 6. So we got to jump over pi over 2. We got to exclude that, but it's still positive up until 5 pi over 6. Okay, so that includes this piece and this piece, excluding this asymptote in between. Then if we jump across to the next solution, that was at 7 pi over 6. That goes up until the vertical asymptote at 3 pi over 2. We got to exclude that. But once I jump over that vertical asymptote, we're still positive up until the last solution at 11 pi over 6. And I realize that gets a little complicated to write once we start introducing some asymptotes in there. But that would be the correct interval notation for when this is greater than 0. Okay. So the less than 0 parts are going to be just right before the initial solution. So that's going to be from 0 to pi over 6. It's a little bit easier to write this part, I think, than in between the middle solutions. So everything from 5 pi over 6 to 7 pi over 6 is negative. And then finally at the end, the last solution to 2 pi. So from 11 pi over 6 to 2 pi, everything is negative. And just remember, 2 pi was never going to be included, so we still will end that off with parentheses. Everything else in this context can get a bracket, including the endpoint at 0. Okay. It's going to take a little bit more practice to get used to this process of having the inequalities, but again, with more practice in class, I know you'll get there. Last one that we're going to do is, let's take a look at number 3, and boy, that really kind of bled through there. Let me see if I can get another copy of this so we can take a look at the third example. Bear with me for 1 second. All right, so we're on page 8. Boy, was I prepared. Okay. On page 8, we have cosecant squared minus 1. So let's go ahead and solve when this equals 0. We'll get the solution over the real numbers. We'll graph it, do all those good things. Okay. Last one, cosecant squared minus 1 equals 0. Go ahead and add the 1 to the other side. And because we just did something similar when we looked at tan squared a moment ago, if you have cosecant squared, take the square root of both sides. So you get cosecant x equals plus or minus 1. Here's going to be my hint to you. When you're dealing with the reciprocal functions, as soon as you get that reciprocal alone, change it into its reciprocal, which is sine x. And how do I take this ratio and change it into sine? We're just going to flip it over. And the nice thing is that 1 over 1 is still 1 over 1. And if I flip over negative 1 over 1, it's still negative 1. So when cosecant equals plus or minus 1, sine would equal plus or minus 1 as well. Okay, here's the weird thing about this one. If you go to solve, you would ask yourself, oh, where's sine positive? Where's sine negative? Let's draw triangles everywhere. But it turns out that it's not a triangle question. Because remember that the ratio opposite over hypotenuse, those both can't be 1s. This is going to be a unit circle application. So what you have to do is look around the unit circle. Remember that sine goes with y. And you want to know, when is the y value 1 and when is the y value negative 1 on the unit circle? And it turns out that that happens up at the top point and then down at the lower point here. Well, those coordinates correspond with specific angles. What are those angles in radians? It turns out that the two solutions here are at pi over 2 and 3 pi over 2 in radians. Those are the only two solutions we're going to get. The nice thing is that if we make a mistake in part A, we'll find it, I hope, in part C when we do this graphically. All right, if we're only going to get solutions at pi over 2 and 3 pi over 2 and so on, the exact solution over the real numbers, don't worry too much about this, but it's going to be pi over 2 plus pi n, where n is any integer. We'll focus on that a little bit more when we talk about this in class, but that would be kind of what's called the general solution over the real numbers. Let's move on to solving when does, what does this look like graphically? So what I have to type into the calculator graphically, how am I going to type in cosecant? Well, cosecant is 1 over sine. So you're going to do 1 over parentheses, sine x, close parentheses for the x, and square that. Okay, that notation represents cosecant squared. And I know this is going to look weird, but if from that I subtract 1, that -1 doesn't belong to the denominator according to the calculator. Okay, so that -1 is in a good place right now. I'm going to maybe just shorten up that window a little bit. The y max, I'll just bring it down to 5 or something like that. If I hit graph, here's what the graph looks like. And hopefully this is what we kind of expected, that we get just 2 solutions. The first one at pi over 2, the second one at 3 pi over 2. So let's go ahead and sketch that. Now here's the thing though, just like we saw for the graph of tangent, the graph of cosecant has its asymptotes as well. We have an asymptote actually right away at 0, and then at pi and at 2 pi. As we do more with graphing later on, that will become very apparent. Why do we have asymptotes for cosecant? It's wherever sine is 0. Sine is 0, at pi, at 2 pi, so the reciprocal function is undefined in those locations. All right, now that I have my graph, where is this greater than 0? Well, it is greater than 0 at, first of all, you can't include 0 because there's no value there at all. But it's greater than 0 for everything from 0 to, all right, remember the solution's at pi over 2, right? Here's the weird thing. At pi over 2, we're equal to 0. Oops, I didn't want to draw that in. Okay. We're not greater than 0 at pi over 2. So we have to stop there at that solution. We don't want to include that. But then everything from pi over 2 to pi is still greater than 0. It's above the x-axis. All right, then we got to jump over the asymptote, right? At pi, then where everything up until 3 pi over 2 is still positive. But I don't want to include 3 pi over 2. And then finally, we stop at 2 pi over here. So this very long solution set is where this function is greater than 0. Okay. And for the last piece, solve when this is less than 0. You're going to love this part. It's never less than 0, right? It never goes below the x-axis. If it's at less than or equal to, I would have included just those 2 points where it equals 0, but it actually is never just purely less than 0. Okay. So next time we're in class, we'll do a lot more with solving of equations. We'll try and get a little bit more context to what this general solution is all about. But my main concern right now is that we know how to get the solutions really over 0 to 2 pi and then check in on some of those things graphically. All right, that's it for your day 4 notes. Let me know if you have any questions next time we're together.